Hi. It's very warm in here. So much about wireless technology. Look at this. So I think you've almost finished the well defects up to somewhere here. How to avoid hydrogen cracking, because did you cover this slide?
Hydrogen cracking?
Oh.
Can you show before this one?
I think I was told that somewhere here.
Yeah, he showed it.
Yeah.
He showed this one.
You've covered that, and you've covered this one as well. What I wanted to, to say here is a main classification of the well defects are when they occur, and while most of them, and function of that, they are called hot cracking, hot defects, or cold defects. And generally, hot means that they appear immediately after the weld is performed, or during the weld. While cold, it means that, and that's particularly important for hydrogen cracking. Usually, it appears some time after the weld has been performed. Sometime hours, it could be even days. That's why it's good for the inspection to wait some period to carry the inspection after, if there is any hydrogen cracking they developed. Right. So you've seen this one, which is the longitudinal root crack, which is common with the shield metal arc. What is another very important aspect is some of these defects, function of how large they are and how they are positioned onto the pipe. In this case, it appears in root. It might be difficult to observe them on radiography. This one started in the heat-affected zone, near the root, and the aspect of this defect has this feathery and twisting lines, which they appear darker. Why they appear darker? Because there is a crack present in there. Now, a very interesting one, which appears with gas tungsten arc welding, inclusions of tungsten. And obviously on the radiograph that we have here are these white spots. Why do they appear white? Because this is very similar to other types of inclusions which you've seen last week. Remember, where did you see a similar pattern, like in this one? What other inclusions might be present? It's possible, for instance, to have some oxides, for instance, alumina, but in that case, if it's alumina, it would appear darker. Why do we have tungsten appearing white here? Think about X-rays. What do they image? What do you image with the X-rays? So you see, this is the actual weld, and inside we see these very white spots, which are inclusions of tungsten. So you've had a very similar slide before, I think. Yeah, this one. So in this diagram, it looks very similar, yeah. But this is slag inclusion. Slag, which originates from where? Do you remember where the slag comes from? And particularly is appears with shielded metal arc. Shielded metal arc. Yeah. So one reason is, obviously, there are four main reasons for which the weld defects appear, and probably first and the most important one is improper welding techniques, which can be poor. A welder that is not experienced enough, or the parameters used in the weld are not appropriate. So with slag inclusions, one of the most common reasons is that it is not cleared between passes. Yeah, remember, the welder must clean very, very well all the remaining slag. But I wanted to come back to this to look at so the first image is rather the same as with the tungsten inclusion, but look at the radiograph. What do you see? How do you notice that something is wrong on this radiograph? Are these dark spots here, yeah? So how do you make a distinction between this slag inclusion and tungsten? Tungsten appears white, the slag appears darker. It is with the density of the materials that are sampled by the X-ray. Tungsten is a heavy metal, so it has a higher density. Higher density means they will appear whiter in the radiograph. It is the same principle with the X-rays in health applications. Our bones on any X-ray will appear how? Whiter or darker? Whiter, because of the higher densities, and the organs will appear dark. So that's tungsten inclusion. Tungsten inclusion, how is it possible to have tungsten inclusions in this? So obviously we're using a tungsten electrode because it's gas tungsten arc welding. But why? This is not supposed to happen. So again, it's poor welding technique. Tungsten is a rather brittle metal because it crystallizes in a hexagonal symmetry similar to graphite. Graphite is also very brittle. So it can break if during the welding it touches the weld pool, and it remains solid because tungsten has a high melting temperature. I don't remember what it is, but it's certainly higher than the temperature at which the welding is carried out. Right. Now back to hydrogen cracking. This is hydrogen cracking occurring in the heat affected zone from the cap pass here. So it propagated all the way through the, almost all the way through the heat affected zone. Here is where the crack stops on our image. We'll see later on, I hope, that the part that hydrogen, the crack created by hydrogen diffusion, can follow longitudinal or a transverse direction. So again, function of which direction it goes, it can be easier or difficult to spot it on a radiograph. And it also, in this example, it propagates through the heat affected zone, but it also can get through the weld for the case when it propagates in the transverse direction. Another example here, so previously we've had a hydrogen crack only through the hose, originating from the cap pass, and in this case it originated. Can you tell where the cracking originated? From in the root, but now it's not in the heat affected zone, it's actually in the weld. Cases where when this it's possible to happen in higher grades steels, because in that case, in order to match the chemical composition of the grade, we have to use an electrode that is made from a high alloyed steel. High alloyed, it means it is more brittle than a low alloyed one, and the crack will propagate through the weld region. Right. Now, remember what we said, we can have longitudinal cracks or transverse cracks. This one is longitudinal. That's how it goes through the weld. In this case, yeah, it can deviate a little bit, making a zigzag. But function of that, and look on the radiograph, it might be quite difficult to observe it. It is here because, as in the description there, it appears as lines of darker density, and they are marked here. You need really a well-trained eye in order to observe this. So that's the hydrogen cracking propagating longitudinally. Hydrogen cracking that propagates in the transverse direction through the weld metal. Can you spot it where that is on this micrograph? This one, yeah?
Yes.
So we have hydrogen cracking. Now, how does it appear on the image? When it propagates in a transverse direction, it can form something that we called chevron pattern. And this is actually very difficult to spot in a radiograph because the cracks, they tend to propagate at 45 degrees, which is actually it's parallel to the marks left by different passes. For instance, this one, and look here, the crack tends to propagate parallel with those marks, and also this one is parallel with the interpass border here. And chevron cracking, you can notice that even better on this diagram. The chevron pattern are these yellow yellow marks on the diagram, and they tend to be parallel with the marks observed from the weld passes. So it is rather difficult to spot them in radiographs because they can be easily confused with with the marks left by interpasses. The transverse hydrogen cracks, they can lead to the formation of a large fracture going all the way through the weld. So obviously this can be detected only by performing radiography, and this is very clear here in this where these two arrows are marked. Again, any crack will appear darker on an X-ray image, but just try to imagine how dangerous these are, because without radiography you wouldn't notice anything because the cap looks very well. Also, if you look at the root, it seems to be a sound weld, so the only way to observe it is by performing radiography. What else have we got here? Solidification cracking or hot cracking. So in many cases it might be difficult to make the distinction between what is caused by hydrogen and what is caused by solidification. Why solidification? During heating, we have liquids. During heating, usually all materials, they expand. During cooling, all materials, they contract. But function of this contraction might be a different function of the phases are present in the weld, and also it depends on the ratio between the width of the root pass and the depth of the root pass. So the larger the ratio between the depth and width, the higher the possibility to have a crack that is caused by solidification. And another name for it, it's hot tear. You notice the word here, hot, because it appears immediately after solidification, so you don't need to wait days in order for the crack to initiate and propagate. Laminations in the pipe. Now, you probably know where these laminations are coming from. What do you think that this, it's obviously from the micrograph that the lamination is this one. Okay? If you look at it, it doesn't appear like to be causing any problems. Well, first of all, what is this? What is this dark line?
Scratch maybe in the...
It's not a scratch, no?
It's an inclusion. An inclusion.
It's an inclusion, yeah. And judging from the aspect of, from its geometry, this inclusion is brittle or ductile.
It's brittle.
Well, however, it might be. We have a lot of manganese in steel, in these steels, so it is very likely that this is manganese sulfide, which is very soft compared to other phases present in steel. And during rolling, it forms these stringers. I think that's how we called them in previous lectures. That's okay. It's present there. But what happened during welding? During welding, because of the stresses that are born during solidification, again, stresses that are coming where from? From the mismatch in the in the contraction during solidification between different phases. So by imposing residual stresses on this lamination, it will lead in time to what? Well, add a prefix to this one, delamination. It will tend to open. So let's say this is our stringer, or laminated, because it appears laminated. Now, because of the stresses, let's say it's very close to the weld, this is in the heat affected zone. Because of the stresses, it will tend to split like that. So it will form here a crack. So laminations will lead to delaminations, eventually forming a crack, which is, if it's in the heat affected zone, that's pretty bad because it will tend to propagate. And obviously, from this micrograph, judging by the microstructure that we observe, this is the weld pool, this is the weld. This region appears darker, so we know that this is the heat affected zone. So we have an inclusion laminated, which is in the heat affected zone. So it's very likely that this will be an area where delamination will occur. Okay, what else do we have here? Slack intrusion in the root bit. Again, why do we have slack there? Because the weld hasn't been cleaned properly to remove all the slack after welding, which is difficult because the skills of the welder also depends on the access to the weld, and there are situations when the access it's very difficult. And try to imagine that the welder also must find the position in such a way that the sparks from the weld, they don't fall on him. So performing a sound weld, it's really difficult. That's why, at least that's what I've heard, very skillful welders are very well paid, and they probably deserve that. Now, other defects also from pipe handling, if any deformations occur during handling the pipe, during lowering in the ground, or if the stresses imposed are too high, then fracture will occur. Another situation, if there is earth movement while the pipe is in the ground, and I think the next slide will show us that. Yeah, but what do you notice? Where do you see this crack propagating? What region is? It is the heat affected zone. So in most situations, the crack will tend to propagate in the heat affected zone. No, that's very interesting, because the next topic will be repairs, and also repairs carried out to correct improper welds. Actually, these repairs might lead to catastrophic defects like hydrogen cracking. In this image, hydrogen cracking was caused by an improper repair weld. In the past, these repairs, in order to perform them with speed, these repairs, particularly the repairs carried out for the root bit, they were carried out just in one pass. And in one pass, that's very likely to introduce high stresses in the heat affected zone, and the heat affected zone will contain hard and brittle phases. So that's why nowadays most of these repairs that are carried for the well bit, they involve at least two passes. The role of the second pass is to produce a little bit of tempering in the heat affected zone created by the first pass. And you can see here that judging by the color, the heat affected zone was very intense in the area near the root. So the crack that we have here propagated through the heat affected zone, and it was caused by an improper repair. Other improper repair, just look at this image and it's very clear to see what happened. As we look at the micrograph on the left hand side, there is the haze is very intense. So because of that, look, crack propagates all the way in the heat affected zones. Again, another one caused by repairs. What else do we have here? Stress corrosion cracking. Now, stress, as the name suggests, stress corrosion cracking, you must have a few, you must have certain elements there for stress corrosion cracking to occur. First, stress. There must be some stress present. Stress, which can be residual stresses that are present in our case, in the heat affected zone. What other factors must be present? Corrosion. There must be a corrosive agent, something that produces corrosion. And if these factors are met, we can have stress corrosion cracking, and we also must have a sensitized microstructure. And this is the case, it appears with Down's gas. Down's gas, it's coal gas produced from coal, which also contains a lot of hydrogen, so it might lead to hydrogen cracking, and many other components which are corrosive to the pipe. So the requirements for stress corrosion are there because we have a corrosive environment. And these micrographs show clearly that's the inner part of the pipe. What do you notice? A lot of corrosion cracks at all places, and obviously one of them eventually propagated all the way through through the pipe wall. Okay, and the last aspect, well, welding the weld outlets onto pipes, it's generally difficult, and the material from the weld outlets might not match exactly the chemical composition of the pipe. So because of the geometry, it might, in most cases, the weld defects that are found in weld outlet weldings are lack of penetration. This is the weld outlet here welded onto the pipe. We're looking at a cross section, so it has been cut all the way through. Okay, so I finished this, and I think I'm going to start the next lecture, which is repairs. And we don't have time to cover too much, but I'm going to start it. And this is funny. I don't really know what it means. You'll have to ask Professor Bull. But obviously, this is history, how they used to do repairs on pipes, probably in the 50s, in the 60s. So there are a lot of wedges there. I don't know what are they, so please ask. Sorry?
Plugging the leak.
Plugging the leak, it might be, yeah, I don't know. However,
It's always the wooden.
yeah, I suppose so. Probably some wooden wedges and they bolt them into the pipe too. Huh? Yeah? Well, that's okay. I thought this was history.
No, it's not history. In some countries.
Do they last long?
No. Yeah, it depends.
it depends on the pressure. Okay. A few considerations about repairs. So first of all, repairs, expect that they are not cheap. And for onshore ones, the cost can be high, but for offshore ones, the repairs are very, very expensive. So serious consideration must be taken into account. Do we really need to perform any repairs or not? And you'll see later on that the first option, we have, I don't know, 8 or 9 options how to perform the repairs, and the first one is do nothing, which doesn't actually mean do nothing. Some actions must be taken, but that's mostly on the paper, perform some calculations. And in relation to what I've said, there are some defects which we would consider them as minor, which can be accepted based on this fitness for practice. If we accept some defects, but obviously we need to know many details about them, how extensive they are, what is the stress state around these defects, etc., then perhaps we can do nothing, or some simple dressing, like for instance a weld to remove the high stresses. So if you have a defect, a gouge or something on the pipe surface, let's make it like this. Okay, then the option is to either grind it to some extent, and if grinding is enough, then what you would get would be something like this. So this is actually quite a good solution, but remember, this is not an extensive defect. This is a good solution because here we have sharp corners which act as stress racers, while after grinding you create a more rounded shape of that defect, so it won't pose a problem. Obviously, with grinding, there is another problem. Do not do that extensively, because what happens, it will raise the temperature in the pipe, and it will induce, it might induce phase changes. But if the defects that we're considering are extensive, the options generally are to replace that section of the pipe, or an easier option is to downrate the pipe. Downrating means that you reduce the maximum operating pressure of the pipe in order to cope with the new conditions in which now we're considering the presence of defects. If we decided that repairs are needed for our pipes, then we need to know, and as you can see from these ideas on the slide, we need to know pretty much everything about that pipe. Details regarding dimensions, grade of the steel, how the pipe was manufactured. Operating conditions, particularly the conditions that led to damage that now we need to carry out, and that might be corrosion, and comprehensive details about the damage. What type of damage is that? How extensive, and where does it occur on the pipe? The product specification. What is the use of the pipe to carry what? Is there any corrosion, any anti-corrosion protection? Cathodic protection, is there a cathodic protection present? The conditions in which the pipe was buried into the ground. For subsea pipelines, what is the depth of the water, what is the temperature, and also the current conditions and the seabed condition. What is the condition of the seabed? Is it a sandy one, a rocky one, and so on. What kind of damage that we need to take into consideration for repairs? Well, first of all, damage that was caused by manufacturing or that occurred during construction, and that includes welding. Yeah.
Previous slide, why do we need to know the conditions that you just highlighted for the repair?
Which conditions?
These pipe details, this pipe burial condition, water depths. Why do we need them?
In order to assess what caused the damage, and can we continue to operate the pipeline in the present conditions? Because if we cannot, if the damage will proceed with a high rate, then we probably need to do one of the two options: replace a section of the pipe or donate the pipe. Another major factor is corrosion. Corrosion which occurs internally or externally, and mainly the sour cracking. That's the case, which again, it depends on what is the pipeline used for, and any mechanical damage which generally occur during handling of the pipe. So, regarding the extent of the damage, we need to consider, is the pipe leaking or not? Because if it's leaking, we might take the option, well, that's not a nice option to actually stop the operation of the pipe. It's expensive, nobody likes that. So we can carry repairs while the actual pipeline operates, and you'll see later on how this can be done. Immediate repairs can be carried out by replacing sections of the pipe where leaking might have occurred, and for that you need to use a bypass. So if you have a leaking pipe, let's say that's the pipe, and you have a leak somewhere here, then the option is to bypass. So on both sides of the damage, connect this bypass. It could be by welding, and then you actually achieve you allow the flow of the product inside through this bypass, and then cut the section of the pipe out. That's one option, which is quite expensive. Right, so here we have how many? 12 techniques for approaching the repairs. The first thing is do nothing. But remember, in order to decide that there is nothing to do, we need to perform some calculations, and it's exactly this. What is the extent of the defect? Can the pipeline operate with the current damage under the current conditions? So again, a fit per purpose assessment must be carried out, and if indeed there is no need to do any major intervention, then we decide that there is nothing to do. The second option is we don't do anything in terms of going on the site and perform some repairs, but we continuously or regularly monitor the defects. Monitor the defects to see if in time, for instance, every weekly or monthly, monitor a defect that is present somewhere to see did it propagate it under the conditions in which the pipe operate, and after monitoring for a period of time, if the defect doesn't extend at all, then we can stop the monitoring and say that the pipe will safely operate in the future. Downrate and also monitor the defect. So if our calculations predict that under current operating conditions that defect will lead to failure, then the option is to downrate the pipeline, reduce the maximum operating pressure in order for the pipeline to cope with the new yield strength of the pipe, which was now reduced because of the presence of some defects. Option number 4 is remove the defect by dressing it out. One way to dressing it out was this one, which we said do some grinding if it's not a very extensive defect, do some grinding, or some welding can be performed also to put the material back. Number 5, a little bit more complex repair, is epoxy grouted sleeves. You'll see the epoxy grouted sleeves. They are later on. You'll take all of this in details. Do we have an epoxy sleeve somewhere here? This is dressing. Yeah, these are the epoxy sleeves. Epoxy sleeves, well, 2 shells which are made from the same steel as the pipeline, they can be welded or they can be bolted, as in this image, and the gap between them is filled with epoxy resins. And the test shows that they are very good repairs because during the hydrostatic testing, neither of these repairs failed. Actually, the pipe will fail in some other areas. Use glass fiber reinforced composites as repair bandages, and I'm just presenting them briefly now because Professor Bull will go in details with you. Where are they? This one, for instance, the clock spring repairs. So these are made from glass fiber reinforced composites, and they you simply bandage the pipeline in the region of defect. What else? Welded patches and half shelves. Half shelves, similarly to the shelves that we've seen in the case for grouted sleeves. Shells and hot tap fittings. Hot tap fittings means that they are connected onto the pipe during the pipe operation, so we don't need to stop. Cut out pipe sections and replace them with, as I anticipated there, with bypasses, or they're so-called stopples. Well deposition repairs. So, for instance, in this case, we could apply a minimal deposition repairs, but again, because it's a weld, the same considerations must be applies like for any type of weld. What else? Temporary leak clamps or plugs, and finally permanently leak clamps or clamps. The temporary ones are used for generally for high pressure pipelines and for low pressure, but they can be left permanently once installed. Okay, so I'm gonna stop here. Any questions about this? Okay. Are you okay with the assignment? Is it going well? Yeah. Yeah. Oh, well, yeah, check that. Yes, check that because that's a serious thing. And,
So what's the highest rate of plagiarism? 20, 50?
well, you know, it should be zero. But there is a thing.
It cannot be zero.
There is a thing. No, you are absolutely right. And for instance, there are typical expressions which everybody uses. And I'm going to give you an example with 3 words. Surface contact fatigue. This is fatigue in contact. This is the term that, and if you submit your work with that, it will trigger like you took it from somewhere. So, in my opinion, this should be taken with a pinch of salt, and you really need to look at. So, if it's 2 words, this is stupid to consider that 2 words together you took them from somewhere. But you know, if it's a whole sentence or a whole paragraph copied
I
and
have,
pasted
for example,
from
some of the words that say it's plagiarism, so copied from somewhere, showing.
yeah.
For example, in one paragraph, there are just 2 words here, 2 words here, 2 words here, something like that.
Then if you have something like that, there is no need to worry. And generally from my experience, everything below 15% or sometimes maybe even 20%, it's I would call that software artifact.
Then another thing is there are some things which are general. For instance, when you're like talking about structure,
Yeah.
the brain, so it highlights them because maybe they have been talked
Everywhere,
about
they're used
Yeah.
everywhere.
So for instance, you make a sentence.
and you're saying the brain grows and then at this point crystal
Yeah,
becomes
or
a
you
brain.
make a sentence. Formation of martensite should be avoided. Well, probably this
has been written so many times.
in so many papers. So,
Yeah.
yeah.
Struggling with changing the word.
But I think, as I said, if it's below 20%, it's probably not an issue, because up to 20%, you probably collect this 20% from 3 words there, 2 words there. So make sure it's not a continuous sentence like this. And everything that is not your sentence, if you
We need to cut it off.
if you take from a paper something that somebody else said, give the citation. Yeah, give the citation.
Yeah, we do, but like we said, sometimes it's your own words, but still it highlights them because
Yeah, that's right. But if you give the citation and you put that in quotes like this, and then the citation here, then even if the software takes that into consideration, that should be discarded because you put the citation marks and you
But
also
anyway, it will count as a plagiarism.
no.
Well,
No.
software does it highlights it.
The software highlights that.
We'll check it.
Yeah.
It will.
No, but the markup.
The software marks that, but the marker of your work should ignore this
Oh.
because it's not correct. But obviously you don't use that too much.
Yeah, yeah.
Only if it's something. So you would say that only if it's something really unique, that somebody said something so unique that.
Yeah, needs to be put in those exact words.
Yeah. For instance, Richard Feynman, he said there's plenty of room at the bottom regarding the nanomaterials. So if you present something regarding nanomaterials, you can put that in citation marks. Feynman said there is plenty of room at the bottom. So you don't need to change the words. It's quite a famous saying, so you can quote that.
The rest is paraphrased if you need to.
Yeah. So this is actually not a solution. Just copy it from somewhere and put it in quotes. That's wrong. It's wrong. So only if it's something unique.
Okay. Thanks.
So, Dr. Riley, I want to ask you something. Can we put a banded pipeline into the flexible test rig?
Into?
The flexible test rig. I want to do the fatigue. So the specimen should be flat, right?
Yeah.
No, like this.
It's rectangular in cross section.
Rectangular
Yeah.
section.
Yeah.
So what I'm going to do is I want to do a fatigue analysis on the that specimen that, for example, I have a specimen here.
Yeah.
And this is the welding.
Yeah.
I need to bend it first. I need to put it on the
Yeah.
plastic regime,
Yeah.
and then I do the fatigue test.
No.
Cannot do that.
Why would you do that?
Yeah, I need to see, the position of the large deflection of the,
But if you bend it,
yeah, by bending, because external load, for example, buckle.
but that doesn't really reproduce as a buckle.
So, for example, if your pipeline is like this to the buckle, then your weld will. Or maybe I can just see how it behave under the 3-point bending test. Not the fatigue.
Just bending this before starting the test, you don't achieve anything because that bending won't produce any damage. Because remember, you're not testing a pipe,
Yeah.
you're testing
Specimen.
a solid piece. Yeah.
Solid piece.
So the pipe has a wall thickness,
Yeah.
and buckling, it's a problem if you bend the pipe.
Mm.
Buckling doesn't really have a meaning if you bend a solid material. It must be hollow,
Yeah.
you see, because the geometry also
But what
influences that.
happens if the weld is very small?